Generally, I'm not particularly fond of the word networking to describe what I do. Because when I tell people I do networking, generally they think of this, right? They think of cables and racks and optics and switches and routers. And this is generally a huge part of networking. And it's a really big part of what we do, and we're really, really good at it. But if this is what you think networking is, well, like every CDN does networking, right? Because they have to. It's part of the name. And part of building out a global infrastructure is actually building out the networking as well. And we do this as well, but like we also do something else entirely, and that's what this talk is about. So before I go into what we do, every time I mention networking, it's within the context of CDNs, right? And there's a big problem within the CDN industry, which is that in many ways, networking doesn't really have any obvious products and features that distinguish between CDNs. Like, if you're a CDN customer, how many actual networking features do you look for in a CDN, right? It's probably not the thing that is most appealing to you as a customer, right? And like, is it geographic reach? That's kind of networking, right? And if you actually go to any CDN website, and I checked, and if you search for the word network is a map. And that kind of makes sense, because if you were to map the actual relationship between RTT and the number of POPs, right? You guys kind of start somewhere around there, right? Because all traffic is going to origin. And the beautiful thing about a CDN is that as you keep adding the number of POPs, RTT keeps getting lower and lower. Now the problem with this is that at some point you reach this kind of asymptotic limit as to how close to end users you can actually get, right? And I don't know exactly where that limit lies, but it's somewhere like as n tends to Akamai or something, right? And people sell you this as if it's a feature, and it kind of is until it isn't, right? Because there are other metrics that matter. And they don't actually go quite as nicely with the number of POPs, like stuff like hit ratio. Cache hit ratio will necessarily go down as you increase the number of POPs. And I'd argue that most of you are somewhere around there, right? At some point, you actually stop caring about the number of POPs because you already have sufficient geographical footprint, and you start caring about other stuff like instant purging, which gets harder and harder as the number of POPs increases. Another kind of thing that sometimes gets flaunted around as if it's a feature is bandwidth. It kind of is. Like, from the customer perspective, I don't really know how much you really care about bandwidth. It's just a number. I mean, if I show you a bandwidth graph, like, what does that mean to you? Well, yeah, so I'll get back to that. But the proportion of bandwidth itself, once you are honest, I would argue that you stop caring. Now, where you are on this curve depends on how much traffic you have. But the truth is, economies of scale and the fact that capacity keeps getting cheaper means that at some point you will be on that curve. And once you are on that curve, you will stop caring. So it is a feature until it isn't. And after it's no longer a critical feature, it becomes just market signaling, right? And there's other stuff that some people sometimes ask about, like IPv6. IPv6 is something we're working on. It's on the roadmap. It'll be out soon. But the truth is that if IPv6 were a really big thing and everyone were asking us for it, we would have done this long ago. And the truth is, if you go to CDN comparison websites, the things that really, really matter are usually developer-driven, right? There's stuff at the application. There's stuff like versionless tables and surrogate key purging. That's the stuff that really drives adoption in CDN industry. And that's kind of a shame. It's a very demeaning view of networking, right? There used to be a time when networking was actually kind of cool. There's this beautiful quote from John Gage, who was a very early Sun employee, which is that the network is the computer. Now, this doesn't actually make any sense nowadays because no one actually remembers what a computer looks like. But at the time, it kind of perfectly encapsulated this shift between personal computing and networked systems, right? But in the CDN industry, that's really not what you have, right? Because networking has a very limited marginal utility. After a while, doing more doesn't actually make it any better. And so for every CDN, networking is just infrastructure, purely, right? It's just something you buy. It's a sunk cost. It's something that has a fixed feature set and just depreciates at a constant rate over a bounded period of time. And that's exactly as boring as it sounds, right? So we don't do any of that crap. For us, the network is the application, right? It's a set of functions that you can expose to services and which you can eventually surface to you, the customer, right? Eventually. So that's what we do. Now, before I go into how we actually did this or started doing this, I'd love to start spinning a story about how we all got into a room and started identifying functions we needed, like stuff like routing and DDoS mitigation and load balancing. And then we went off and we wrote some software. And the software was so good that it kind of replaced all these boxes. And in the process of getting rid of the boxes, we saved a ton of money. Unfortunately, none of that is actually true. And apparently trunsparency is like a new core value of our company. So I haven't been here long enough to truly know how it started, but I have a sneaky suspicion, right? And I think that story is in the exact reverse order. We started with the money, we had it. Arthur blew it all on commodity hardware. And so we couldn't actually afford the boxes. So we sort of had to write the software to implement, frankly, really basic networking functions. So I've actually been assured that this can no longer happen because we have a CFO. But we actually ended up in a really nice place accidentally. Or maybe there was a method to the madness. I don't know. You have to ask Arthur. And so I'm going to go over how we implemented each of these functions by not buying boxes, essentially. So think of load balancing, right? The generic problem of load balancing. And the problem with load balancing is you have this mysterious thing called the internet. And this is the start of every single problem I have in life. And the internet is just throwing you packets at a point of presence, right? And you can think of a point of presence as a router and a bunch of servers underneath. And the challenge with load balancing is to spread traffic equally across your backends, but also that you can actually remove any server at any given time, and you want to do that seamlessly, and you want to keep traffic efficiently and evenly spread, right? And so how do you do this, right? So many of you have to do this with your origins, right? And you can use DNS. You just put the IPs in, and DNS will round robin naturally. Unfortunately, you can't actually do this if you're a CDN. For one, we manage a vastly expanding number of hosts. And so manipulating at that level DNS is kind of hard. The other thing is we already use DNS to load balance between POPs. And so doing POP level balancing and host level balancing in the same infrastructure somehow it gets really complicated really fast. But most importantly, DNS TTL. You don't actually have to respect DNS TTL. And we interact with large swaths of the internet which have no actual respect for RFCs, right? And so there are large ISPs which actually enforce you a minimum TTL of 30 minutes. And if you're taking servers in and out of production within that time frame, well, connections will just get dropped. So load balancer is another thing, right? Load balancers were made for this. Load balancers are great, except they require state. And state and cost have this horrific function. And so the way you kind of provision load balancers is you look at your network today, and you kind of guess what the existing demand is, or if you actually have graphs, you might not guess. That'd be good. And then you really extrapolate what your projected demand is for the lifetime of that equipment. But God forbid you get that wrong, because if you put a load balancer in place and you get unexpected demand, everything beyond that point is completely unexpected, right? The load balancers will just fall over. So that's not really an option for us, because we're actually exposed to wide area networking, right? We are subjected to DDoSes. We are subjected to huge spikes in customer demand. So what most of the industry has kind of converged on is something called ECMP, which is equal cost multipath, right? That you have a routing table, that a routing table has multiple entries to the same destination network, and that each of these entries points at a different next hop. And so in this example, a flow is coming in and is getting hashed onto the second entry. And so ECMP is really practical because it's stateless. It's just hashing. The problem is, if I'm going to remove server A from production, right, I will just remove it, and something really funny will happen, which is that the routing table will change. And now you're screwed, because the entry that was previously hashing onto B is hashing onto C. And so even though neither of those services was involved in the routing change, because of rehashing, you end up getting a connection reset, right? So this is a bit of a problem, but this is standard best practices for most of the industry, right? So what we came up with was we just wrote something, and internally it's called failed. And failed just builds upon ECMP, because ECMP fundamentally is okay. It just happens to behave really badly in a corner case. And so what failed does is it inserts ECMP entries into the routing table. But what it does is it uses fake next hops. And the idea is that these fake next hops, even though they don't exist in the network, they encode information. And in particular, the information we encode in the virtual IP addresses is the server we expect the traffic to end up in. Now, the interesting thing is that we don't ever change the routing table, because you can't, because otherwise you get rehashing, right? And so imagine a flow coming in and hashing onto the first table entry. It will get hashed onto A. And now imagine that you just want to take A out of rotation. The interesting thing is the way we're steering traffic is not through the routing table. It's through the ARP table. That's the only thing we actually manipulate. So in this case, it's going to MAC address AA. And I'll explain what that means in a bit. But OK, so keep looking at the ARP table, right? I'm just going to remove server A from production. What that does in practice is that just changes the MAC address associated to that IP. And the interesting thing about it is that the MAC addresses are also bogus, but they encode two really important pieces of information, which is what the new server is and what the previous server was. And so now on server B, because it knows what MAC address that traffic is coming through in, what server B can do is start a new connection tracking table. And for any new traffic towards that MAC, it starts inserting connection entries and accepting them. And any traffic it doesn't actually recognize just gets redirected back to the old host, right? So somehow you have a mechanism for flow redirection, so that when you drain, you don't actually get any resets. And if you notice the other entries in the MAC, like in the ARP table, they're all pointing at different hosts. And that's why we have 3 routing entries for failover for server A, so that when server A fails, we can actually equally spread the traffic across the remaining hosts in a data center. At some point, you have to actually stop draining, because otherwise you're just incurring constant state, and you can't keep that forever. So at some point, you just switch the MAC address again to the steady state behavior, which in this case is just BB. The cool thing about failed is that, well, you have 2 industry solutions, right? You have ECMP. And the problem with ECMP is the minute you drain, there is a certain number of active flows that would have naturally decayed over time. And ECMP just kills them all. And if you buy a load balancer, you're slightly better in the sense that all the flows get saved, but somehow you have to incur a constant amount of state, whether or not you're draining the actual traffic, right? And so failed is kind of the trade-off between both, right? That you have this draining time which perfectly mediates what you're willing to accept. And so you start incurring state up to the point where you stop draining, and from that moment on, all existing flows just get reset. And if we reduce the draining time, we approach ECMP behavior. If we increase it, we just approach the behavior, like we get feature parity with a load balancer, right? And load balancers aren't cheap. And we just do this all in software. So the other features I'm going to go through now is routing, and it's kind of a similar proposition, right? That routing is normally viewed as something very simple. So simple that everyone does it in exactly the same way. So the way every CDN builds a POP is they buy a router, they get these routes from providers, they install it into the local FIB, and then every server in that data center will just use a default gateway out. This is like networking 101 type of stuff. Except that routers aren't cheap. They're like $500,000 expensive. So for the sake of argument, let's just say no. And so how we built Fastly is by not buying routers, right? Instead, you buy a switch. Now, the limitation of a switch is that it doesn't have enough FIB space for you to inject routes into. But the switch is perfectly capable of receiving routes, right? And so that's what we do. We receive routes, and we send them down to the servers. The servers are perfectly capable of doing millions of routes, because that's where Archer spent all the money, right? So this is perfectly fine. And so the server just injects multipath routes into the fib. And so there's some magic here in that you do need a distributed system to spread around network configuration information to set this all up properly. But the beauty of it is that once you've done that, the server can directly offload traffic into separate providers individually, right? And this is something that a router would have never given you, because a router gives you a single best path for all servers in a data center. And so we did this, instead of buying routers, just buying a ton of these. Which, I mean, I put something that looks like this price. It was actually way lower than that, but putting the real price just gets embarrassing after a while. And so every cache actually has 2 million routes, because this is 4 full BGP tables from 4 different switches, typically in a POP. And again, you can do cool things, right? We wrote a utility, which is SDPing, which essentially does a ping through each parallel path. And then you can start comparing the latency between providers. Or if there's a meltdown in the transit, you can very quickly identify which transit it was. And so this actually brings up a really interesting possibilities, right? Which is routers always choose a best path. But best path depends on what kind of traffic you have. You might have a shortest path that is very limited in terms of bandwidth or very costly. And you have different types of service in a CDN, right? So a video might actually benefit more from having low jitter and high bandwidth than necessarily the quickest RTT. And in a normal CDN case, you actually have to put all traffic in one of the paths. And in our case, we have a very interesting property, which is every flow is one system call away from a path change, right? So in theory, we can actually put the first 64 kilobytes of your flow on the fastest path, and then offload you to a higher bandwidth path. And if this sounds familiar, I mean, if you're previously from the telco industry, this is a pipe dream of the 90s, right? This is quality of service. And we can actually do that because we have that data at the application. So now I'm going to go into DDoS mitigation. And this is something we never really talk about publicly because we give a shit about the traffic. So normally the DDoS case is actually quite simple, right? Is that you have a POP, and you have some providers, and then you have some links. And the links might actually have different capacity. It doesn't really matter. Sometimes it does. And then you have an attacker. I have no idea why OmniGraffle chose that shape. And then you have some other links, right? And the nature of DDoS attacks normally is that the attacker has more bandwidth than you. Because that's how nation states work. And because of this disparity, it's actually very easy for them to just generate a ton of packets and send them your way, right? And this is where most of you finish. But we can do a bit better than that. We can actually use BGP. And so BGP has this thing called communities, which you can tag routes with in order to tell your provider to do things for you, essentially. And so we can actually tell a provider to withdraw a route, right? And so that route ceases to exist. And the attacker actually has limited influence in how this plays out, because they may control edge hosts, but they don't necessarily control the routing infrastructure. And so in this case, if they send packets again, it might be ingressing through a higher capacity link or a provider with which we have a lot more links in general, right? Of course, if you haven't set this up, if you haven't talked to your provider to get you an actual list of communities, because the public ones are not the full set, you're screwed. But also, this is quite simplistic, right? Because you can still get an attack which overrides any individual link on a site, or any group of links on a site. And this is where being a CDN kind of gets almost fun, which is that you have other POPs, which are bigger, and they have other providers, or the same providers with even more bandwidth, right? And essentially, you can actually announce routes to an attacker in an attempt to shed the load. And the really cool thing is that all the BGP tricks you do from one site, you start doing in a coordinated fashion from multiple POPs, right? So we can do this and force an attacker in through a specific link. And this gets really interesting once you know the geographic properties of the networks. So that particular link between China and Telia happens to be the shortest RTT link, and also happens to be very limited in terms of capacity. So if you manage to force an attack through a very tight space, it ends up trashing all other traffic over it. And so you can actually start doing externalities properly, right? It's amazing how quickly attacks stop when you affect something that is of critical importance for other people. It's amazing. I feel really sorry for like financial traders in Beijing or whatever, but so there's that. Of course, if you don't have large off-peak sinks, you're screwed. And this is where the value of bandwidth, the absolute value, is almost meaningless without context, right? That you can have a lot of bandwidth, but if it's all spread out in very small chunks around the world, it doesn't actually help you in this situation. But that was a really simplistic view of a DDoS attack. And so what often happens is you don't have one attack going on at the same time. You have multiple because of botnets and stuff. So every time you like press remind me tomorrow on a software update, this is what happens. But again, it's simple because we have lots of POPs, and we can arbitrarily inject routes for different POPs in different regions, and we can target it to specific places, right? And this is cool. This is kind of a standard list of things that something like a scrubbing service would provide you, right? But we do it naturally. Now, the problem with this is that you have the internet, again. You have lots of POPs, and each POP generates a ton of routes. And so managing this becomes crucial in a sense. So if you can't do arbitrary route injection, or you can't do remote triggered black holes, or you can't do policy updates, you're screwed. But even then, if you do all of these, right, if you can't do them globally, if you can't do them consistently, or synchronously, or instantly, you're really screwed. And so this is where most people find themselves, right, is that even if they know this, they can't actually take advantage of that capacity. We kind of solved this problem a while back, which is that we have a logically centralized policy. So this isn't a single point of failure. This is just a distributed system from which all routing policy in Fastly emanates. And the idea there is that operators only interact with one policy, and when that is shifted, like when you push, you essentially push everywhere at the same time. And this has a very nice property that to control an Anycast network, this is actually essential. And the way we interact with the tool is, well, via GitHub. We actually have a workflow tool that when you change the policy, it automatically stages the difference, the policy change. It calculates the routing changes and automatically opens a pull request. Obviously, if GitHub goes down, it's just Git, right? But this is very powerful because a lot of these routing changes are hard to do programmatically because there is intent. And so you need the peer review to actually not screw it up. And so BGP is kind of cool in the sense that it's just a graph, right? And you can remove and add adjacencies anywhere. And so the very tool that does like DDoS mitigation is the tool that assists you in optimizing performance for like an Anycast network. And so you can imagine that if the blue ISP is going to the furthest POP away, we can literally remove the adjacency in the middle there and push the blue ISP to the closest POP. Of course, in the process, we might screw it up for someone else. And BGP in that sense is kind of inherently unstable. But this is a trade-off, right? And the important thing is just to control it, because then you can start doing improvements. And in general, like why does all this matter, right? Other than like we drop less traffic and we choose better routes and we absorb more attacks or whatever. Like that's kind of numbers, and in the long run, it doesn't mean much. Like time is very unforgiving with numbers. I think even though I stated that we didn't start from a guiding principle, we didn't do a top-down thing, all of the things I talked about have this fundamental theme, which is resource pooling, right? And resource pooling is a really important concept in computer science, that you can solve any problem more efficiently and cost-effectively and scalably by just taking a collection of resources and making them act as one. So if you think of load balancing, what is load balancing? Well, it's really simple. It's just you take a collection of servers and you make them act as one from the outside. So when you actually contact our POPs, it looks like you're talking to an IP. But that IP is actually belonging to a host of servers, which makes our life really tough when you ask us to debug something because we have no idea where it ends up, because it's perfectly pooled. Routing as well. It's just the action of taking a collection of providers and mirroring them down to the hosts as if they're a single virtual link. And same thing with the mitigation aspect, right? That you take something that typically works in isolation and you make a bunch of them work in unison against a common threat. And this kind of should sound simple if I've done my job correctly. And it really is, right? But you have to ask yourself, like, if this is so simple, why is no one else kind of doing it from scratch? And part of the problem with this is that they can't. Because it's really, really hard to change once you go down a certain path. And like the anecdotal kind of story I have for this is like, think of packet switching. Packet switching is really brutally simple. It's just the thing about taking a stream of data, dividing it into packets, and statistically multiplexing it across circuits, right? And so packet switching is actually a form of resource pooling, that you take a bunch of circuits and you make them act as one. Like packet switching was so simple, it was actually invented by two people at the same time, right? One of them was British, and the other guy got all the credit. But the guy, like Paul Barron, who got all the credit, he actually tried to sell this to AT&T. And at the time, AT&T said it was completely unfeasible, right? To divide voice into packets would be literally crazy, as you can tell from your phones with internet. But yeah, but they weren't actually wrong, right? It was completely unfeasible for them because they had built an architecture entirely around carrying voice. So for someone to tell them that packet switching was more effective was the complete antithesis of what they were doing. And it took them over like 30 years to actually get into packet switching, and they still don't do it very well. And this is where Akamai kind of finds itself, right? That they're under the same illusion, right? It's the illusion that you're providing a general purpose service only to find out that you have a single purpose architecture. And a lot of the CDNs are actually going to find this out like 2-3 years from now because your use cases keep changing and they can't, right? Because for them, this was all networking was ever meant to be. It was a sunk cost. And now it's really hard, right? It's really hard to dig yourself out of a race to the bottom. And so if you ever need to change anything, they are literally screwed. But not for us, right? Like, I think realistically, we actually have a fighting chance of being able to like redefine who we are based on what you need us to be. Like, if you think about all like our design choices and our trade-offs in the networking side of things, like they're just software, right? Take questions. Anything?
That was beautiful.
Thank you. Thank you. We need a mic here, or you can just ask the question and I'll repeat it.
Do you see at some point in the future moving off the dedicated switches, the Arista switches, to something more like a white box with SDN?
The answer is yes. So the question was whether we are looking at the future without relying so much on the Arista functionality. The truth is that a lot of the functionality we use, actually almost all of it, is completely commoditized, right? The ability to manipulate ARP entries and a lot of the associated stuff is totally fine. Like you have vendors like Cumulus, so from the switch operating system side, which are really interesting. There are some like quirks around that, which is, well, you kind of still need support, right? Unless you have dedicated capacity to look really deeply into the switch, there is stuff that you can't chase. And the amount of bugs and peculiar behavior that some of this hardware has is something that you don't really want to bear the cost of, right? I don't want to have to know the deep internals of a Broadcom chipset. It's not something that particularly interests me. Like at scale, it's something that might become practical. And at that point, having Cumulus and stuff like that is really nice. But it's something that will take a lot longer, I think, to kind of iron itself out. Anything else? I have no idea, because, like, come on. Yep.
Any plan to connect to exchanges? How do you?
Oh, so is the question peering? Okay. So yeah, peering is an interesting case because peering has an associated cost which is not obvious, which is the cost to manage a lot of individual connections and people on an exchange who do not have a NOC and stuff like that, right? So it's much easier for us to interconnect via transit than it is to have started interconnecting via peering. We are starting to do peering. This is on the roadmap, and if you have any interest in that, we should talk. But there is this illusion that peering is cheap. And it is depending on port count and capacity and stuff like that. We also had some architectural limitations around the fact that, we're a switch. So everything I talked about was layer 2. But I think we are pretty much almost done with that. And so now we're starting to look into peering and offloading a lot of traffic via peering. The one thing about peering that is interesting in my mind is that a lot of the providers that you think have a lot of capacity have it almost purely on peering. And so if the peering fabric goes down, you don't actually have redundancy through the other providers. And we did this almost entirely the other way around, right? That we saved a lot of money on the equipment, so we could actually buy ourselves in a lot into transits. And that means now peering is an accessory that we can actually choose for performance reasons rather than just cost.